Welcome again to another session. So we're going to tackle something under offsets from the code produced. So this is just some simple notes. So I hope you will follow. This is a great example and somehow a notes you can take for your normal classes. So offsets from the code produced. This is a topic under setting out of simple curves. So linear measurement or tape measurements. Make sure you go and see my other videos that I've made. You will be more educated and follow for more to come. Let's go directly to our question here. So offsets from the code produced. In this method, it is very much useful for setting long curves. In this method, a point on the curve is fixed by taking offsets from the tangent. So that is taking the real points of a chord. I hope you know what is a chord. In the beginning, a chord that can be produced from any given arc, so that can be the longest point from one point to another within a curve. So thus a point A of chord T1A is fixed by taking the offset 1 as T1. So here I've done a little illustration. So A to A1, then where T1 A1 is tangent to this line here to T1. Similarly, B can be fixed by taking offset 2 as B2, B1 and B. The same can be done. So this is just a continuous process. We'll tackle the first and the second, and the other will be repeated actions. So let T1A be the chord 1. So the distance from here to here, that is the chord C1 represented. So in other text, you can see that as L. That will be the length of the first subchord. Then AB is the distance from here to the next point there. We'll see it on the next. This is the second chord, and all the adjacent chords within a given circle or curve. So the full chords are found in between. So we have the first chord, full chord, and then we have the last subchord. Remember that. So these represent the deflection of our first deflection. Will be represented by this deflection at angle. So this is A1 T1 to A. The deflection angle is found here. Within an enlarged diagram you can observe that. So the angle is found there. Then the deflection angle 2 is found on the second point here, the smaller portion. So we'll add this with this. We'll describe that later. Having seen that, so this is just a simple illustration of that from the property of circular curves, and this property is here. So the angle at the center of a circle subtended by an arc is double the angle at the circumference subtended by the same arc. So this is the property of simple curve that we are talking about here. So from that property, we can assume, given the deflection angle found here, so the deflection angle will be double that subtended there. You can observe that was done here. So this angle is double the deflection angle that we had gotten here. So that is property of simple circular curves. Remember that. So by taking that, our angle will be 2, the deflection angle that was found earlier. So this can be lambda, something of that kind. So but that is just the representation of the deflection angle. So the deflection angle for T1 OA is 2 twice. So that is twice the angle that had subtended it here. So by the property of simple curves. So T1 OA, this is the angle, and that is represented well in this diagram. So T1 OA. This is the deflection angle that we are speaking about. So that is 2, the deflection angle that we had gotten earlier. And then continuing, so by assuming this is the first subchord, so the first subchord is found here. So from T1 to A, so the first subchord C1 can be assumed to be, so the first subchord and the arc, they have a minimum distance in between them. In other words, they can be similar, so it's just a little deviation of the two and you can get the rest. So by that, so by assuming the first subchord found here, so the C1 is the distance from here to here, that is the chord, the first subchord there, is the same as the arc length T1 to where A is, so the arc represented there on that given figure is the same as R to the angle that had subtended it. So let me show you how this angle was gotten from. We go back to our high school knowledge. So proving the arc is that formula. So R multiplied by 2, the deflection angle found there. When you are in high school, given a figure like this, you are told to find the length of the curve, so the circumference subtended by a given angle on some part of a circle that we had there. That is the thing that we are looking for mainly here. So given an angle, this is the knowledge you are supposed to have down there in your high school or even maybe the primary level. So this is the angle theta, this is the r. So I want to calculate the distance found here to here. This was my simple formula derived from that. So it used to be theta over 360, the whole of the circle, multiplied by pi, multiplied by 2r. By simplification of it, these two will divide this and we'll have pi, the deflection angle, then pi r over 180 degree. So this was the formula of the arc length that we used to have. The same knowledge found also in high school. So by changing this figure in let's say this is in radians, so we used to have 1 degree of radian was is equals to the given here. So that was our that is theta over, so that used to be our formula. You can go and check books here. So this is pi over 180 degrees is equals to 1 radian. So by conversion of this, so our formula was theta over 360 pi r. By conversion of these into radians, that means by equivalent this will remain with theta r. So this is the distance that we are speaking about here. So this is the representation or in radians. So multiplied by 1 radians. Then by multiplying it by 1 radians, so this I have illustrated here that simplification. That will be simple like this. So by having this, I go directly and I change my degree here. So in our what we had here on our figure, so our, you can say our deflection angle there was 2, the deflection angle we had gotten earlier, so that can be 2, that sign, yeah. So by representation, by directly inputting that value, so I'll change here the value that was given here to my 2 deflection angle in the real calculation that we are speaking about here. So by having that, I'll have multiplied this pi by what we have in our question there. So this will be 2 the deflection angle multiplied by r. So I've converted this from the theta, the knowledge that you were supposed to be having down there in your primary level. So that's how they got all these knowledge. So by going back here, so by assuming this C1 is equals to R to the deflection angle that was found there, we'll have our equations as follow. So we'll go directly. So by having that, I've done. So this is 2. So these are the chord. C1 is equals to 2, the deflection angle multiplied by R. I want to get my deflection angle. So I want to know what my deflection angle was. So this will be by simple changing here and there. So R will be divided. So by divided by R, then the 2 also will be divided here and we'll divide it here. Then we'll remain with our deflection angle is equals to C1 over 2R. So this is the first formula that we are getting here. So the deflection angle is equals to, so that is my deflection angle in radians, is equals to C1 over 2R. This is the formula that I'm using it here. And then we go back here. So by representation of that, our offset 1 earlier we had said, so offset 1 is the same as the arc length. So here we produce another arc, we do the same. So I want to produce a curve. So here we have an arc that is gotten from the figure T1 to A1 to A. So we have a curve produced here, and the arc length is the same as the offset. So our offset distance is from A1 to A. The same is done. So by repeating what we had done earlier, that knowledge, so 1 degree of radian is equals to this pi over 180 degrees, the same that we had done there. So the arc length 1 to so the arc length A to A1 is equals to, so this is the arc length A1 is the same, so the knowledge that I applied earlier. So by converting this will remain with the theta, that is the angle multiplied by the 1 radian multiplied by R. And in this case our deflection angle here was only the, so we didn't have a 2 here, so the deflection angle was just that, so multiplied by C. So C in this case C1, so this acts as the radius of the figure. So our figure T1A A1, the radius of that figure is represented here. So our radius is the same as the C1. That's why I have directly changed that. So our C1 acts as the radius of the given figure here. That's why my answer directly. So this becomes C1 multiplied by the deflection angle 1. By having that second formula, so here we'll have this offset 1 is equals to C1 multiplied by the deflection angle 1 found here. So this is the simple representation there. By substituting the value of the deflection angle from the equation 1 that we had earlier, and that of the equation 2, so I go directly in this given figure. So my offset 1 is equals to this is the chord length 1 multiplied by that deflection angle 1, and here our deflection angle was given earlier. We had calculated it earlier as C1 over 2R. So we go directly and we change that. So we import that value directly there. So our offset 1 will be equal to C1 multiplied by the value that we had earlier here, represented by the deflection angle that we had calculated, and our final answer becomes, so our offset 1 will be equals to C1 multiplied by C1, that becomes C1 squared over 2R, and that is our first formula. So offset 1 is equals to C1 squared over 2R. That is the main formula that we will be using in calculating the offsets from the chord produced. Finishing that, we move on to our offset 2. And in our offset 2, I've done a little bit illustration here. So by producing a tangent, so this tangent was straight. Then by producing another second tangent from point A, the second tangent will move until here. So by doing that, our value, so here by producing this second tangent, it will be directly linked to here by having that. Let me see if I can do something a little bit here different in this figure. Yeah, that can be more visible. So in a representation of a diagram like this, so here it's more clear. So this is the tangent. The tangent was produced, it was straight from the first tangent point from T1 found there. By having that, our angles subtended by, it's called, this is the equal opposite angle. So the angle found here will be the same as the angle found here on this smaller portion here. But here on our portion here, that is the second deflection angle, as you can see it here. So this is the second deflection angle that is produced. Even here it's done, this illustration is even more clear. So either of the two you can understand. So by having the opposite angle here will be equal to, so this alternate opposite angles. So our first deflection will be equal to the angle that is found there. So our alternate, so this can even be it can be alternate to even directly opposite angles. So but the angle opposite, so here we'll have our angle as, so this is the deflection angle 1. The total deflection angle found in this figure here on the second part where our C2 is found, the total deflection angle will be deflection angle 1 plus deflection angle 2. And that will be repeated to all the other adjacent points. So they will be tangential, so they will be reflecting to the previous one. So they remember that the alternate, the alternate or the equally the opposite, but that so these angles are equal. So the angle found here, this smaller angle here is equal to this smaller angle here, and that angle will be added to the new angle that we have gotten now in this figure here. So the total of those angles will be there. By having that, so our next point will be, you can remember earlier, so our here we had our first deflection angle as C1 over 2R, and then here our offset 2 is equals to, so this offset 1 first is equals to C1 multiplied by the deflection angle that we had earlier. So that is done on the next part here. So our offset 2 will be equal to 2, offset 2 multiplied by these two angle, the addition of those two angles. So that concept is gotten from, so in our earlier, our offset 1 was equal to C1 multiplied by that deflection angle there. So our second deflection will be added to the first deflection angle there, and by adding that first deflection angle there, so this will be as offset 2 will be C2 into brackets deflection angle 1 plus deflection angle 2 found on the diagrams that we had there earlier. We have our first deflection angle as C1 over 2R. Our second deflection angle will also produce C2 over 2R. So that is just a direct, you can go back, you can do that. So this is just a simple illustration. If you repeat, you will get this answer. So by adding these two, our answer becomes C2 into 2R over C1 plus C2. And then offset 3. So these are the fulls, they are produced from the full subchords. The same will be repeated, so the process will be repeated. And I always tell my learners, so we can have a shortcut, and that shortcut is simple as, so in finding the next an example, like let me do the one that has not been done here, like offset 4. So offset 4 will be equal to so the value, so that will be C4 into the offset that is previously. So the offset that is previously was from C3, so that is C3 over 2R, then plus the code on the offset, that is C4 over 2, that is 2R the same. Then even offset 5 will be done the same. So let me rub here a little bit, but offset 5, the same knowledge is used. So offset 5 will be C5, and then again the previous, so that is C4 over 2R plus C5 over 2R, close the bracket. Or you can just directly simplify, so this 2R is common, it will come outside. These are the simple formulas that are gotten in this given equation. So this can, even here we have the formula of finding the last subcode, even the subcode that are there. So the simplest formula is offset n, that is the number of term, is equals to Cn over 2R into the number of term minus 1, that's what I've done here, plus the term that is present, what I've done here. So that is just a simple representation of that method. So offset from the code produced. I know it has been helpful, so you can rewind the video. Where you have not understand, you can ask questions, then I'll post more videos on the similar topics. Thank you for watching. That will be all. So remember to subscribe to the channel, and you will receive more better things to come. Thank you.